Just like the rest of physics, there is a constant system of notation that if you actually use this to communicate about energy and the related quantities, it's really going to help make your work more clear. So we use capital W to mean work, and it's really helpful to clarify that this isn't the same as omega. We've met lowercase omega before. So we use uppercase W to be work. Be careful that you don't think that this is weight. If you want to handwrite it and make it very clear, you can put little bars on the top, and that makes it very clear that it's a capital W. Now, kinetic energy, we use capital K. Now, I will admit that plenty of the times I use KE to specifically mean kinetic energy. One of the reasons that I do that is that we also talk about lowercase k, which is the spring constant. And it's fairly difficult to differentiate between a lowercase k and an uppercase k, and there are many situations where we use both. So one way is to do your lowercase k like that. Ideally, it doesn't look like an R when you do it. And if you want to do your uppercase K for kinetic energy, you can again put like little bars on it to show that it's uppercase. Potential energy, we use capital U. Now, this is something that we're going to put different subscripts on it to mean different types of potential energy. So U with a lowercase g is going to be for gravity. U with a lowercase sp is for spring potential energy. In a problem where you only have one type of potential energy, it's much easier to just call it U, but frequently we will have more than one type of potential energy. Again, this is capital U, but rarely in physics do we use lowercase u. The next one is really important. E_TH stands for thermal energy. So E in general is energy, and TH here is thermal. So if you just use T, that might be clear, except that E sub capital T also gets used for total. So E sub TH is thermal energy, and that's going to be fairly consistent. When you see it written in equations, at least in these chapters, we're going to be talking about changes in thermal energy. So we put that delta in front. Total system energy is going to be E_sys. So this is a way of saying all of the energy that I possibly want to talk about. So this is a standard way that we write that, and again, when you see it in an equation, you should know that this is inclusive. For instance, E system is frequently going to mean the kinetic energy of the system plus the potential energy. There might be a gravitational potential energy, and there might be a spring potential energy. There might even be a thermal energy to think about. Lastly is power, and this one is especially important. We use capital P to mean power. So if you want to write this and make it very clear that it's not lowercase p, you can use a little end mark. So I point this out because we are also going to meet momentum soon, where we use lowercase p. So within one chapter of another, we're meeting uppercase p and we're meeting lowercase p. So please be careful about that. The bad news is we'll also use uppercase p within certain contexts of momentum. The other thing to note is that we never use P to mean potential energy. So if you write P and you mean potential energy, that's going to be very, very unclear. So please use capital P either to mean power or later to mean certain types of momentum. So please be careful about this notation. Something we are talking about now that we also talked about back with forces is the idea of system versus environment. And whenever we're talking about system, that means one or possibly more objects, and this is going to be the thing that you are analyzing. So it could be a ball, it could be a mass, it could be a cart, but whatever it is you're trying to calculate must be part of your system. There may also be other things that are part of your system as well, but it needs to have clearly defined boundaries. So this is something that, depending on how you do the problem, or at least how you define your system, changes how you do the problem. So while we didn't always take the time to define our system when using forces, it's going to be very important to clearly define our system when we're working with energy. Now, in contrast to the system is the environment. This is everything else, in a way, in the universe except our system. And where we care about the environment is going to be external agents. So for instance, a rope coming from somewhere pulling on a box. That there's that tension force that we can think of as an external force acting on our system. So this is our external agent. Now, whatever's in the environment, we are not explicitly calculating, but the environment can cause an external force. So there can be an interaction between the system and the environment, and we'll calculate work based on that. There's no external boundaries to the environment. Again, the system has clearly defined boundaries, and the environment is literally everything else. Last, there's a few new units to worry about in these chapters. The first is the joule, which is the unit of energy. And there's kind of two different ways that this gets expressed. One is a Newton times a meter, and this is easiest to think about work. That work is a force times a distance, force times distance, Newton times meter, that gives you a joule. Another way to think about it, exactly same thing, if we break the Newton into its fundamental units, we see that a joule is also equal to a kilogram times a meter squared divided by a second squared. And with kinetic energy, that's a mass times a velocity squared, so you can see that these units work out too. Now the other new unit is the unit of power, which we won't use very often, but that is the watt, which is energy per time, so that would be a joule, which we just met, per second, or a kilogram times a meter squared divided by seconds cubed. So don't worry about it if this doesn't make like perfect sense to you. Again, really what should make sense is the joule per second.